In this video, we will be talking about Gibbs free energy at standard state conditions. We will talk about a couple different ways of calculating our Gibbs free energy and look at how we can calculate the Gibbs free energy at a variety of temperatures. Gibbs free energy itself is a state function just like enthalpy and entropy. So it only matters where we start with and where we end to find our change in our Gibbs free energy. So we can handle calculating our Gibbs free energy the same way as we handled calculating our change in enthalpy. If we're interested in the change in the Gibbs free energy for a particular reaction, we can look up our Gibbs free energy of formation for our products minus our Gibbs free energy of formation for our reactants. So for our Gibbs free energy, just like with our enthalpy, there are standardized values that we can look up in tables based on the formation of our particular components from the elements in their most stable elemental form. So again, our enthalpy values, our delta H, are based on the amount of energy or the change in enthalpy between our components in their form and the elements that make them up in their most stable elemental form. So it's essentially how much energy does it take to make the molecule from the elements that make it up in their most stable elemental form. So for example, water would be hydrogen as a hydrogen gas and oxygen as an oxygen gas coming together to make H2O. So for our Gibbs free energy, we get the same idea. The enthalpy of reaction is equal to our enthalpy of formation for our products minus the enthalpy of formation for our reactants multiplied by their respective coefficients. This is typically good only at 25 degrees Celsius or whatever the value for the table that you're looking up is. Because unlike our enthalpy and our entropy values, the Gibbs free energy is highly dependent on temperature. So if we're working at a temperature that's other than 25 degrees Celsius, we will need another way of coming up with our Gibbs free energy. The most common way is to calculate our enthalpy of reaction and our entropy of reaction and plug them into the equation that we had derived previously, where the change in the Gibbs free energy for a particular reaction is equal to the change in enthalpy for the reaction minus the change in the entropy for the reaction. The entropy change in entropy, of course, being multiplied by T, and that temperature is in Kelvin. The change in enthalpy and our change in entropy are fairly temperature independent. There is a little bit of variation in our change in enthalpy and our entropy, but it can generally be treated as negligible as long as you're not doing a very large temperature change. So as long as you're under a couple hundred degrees Celsius, our change in enthalpy and our change in entropy can be generally treated as negligible. If you really need very accurate values for something, what you could end up doing is calculate the change in enthalpy and entropy at the particular temperature and then plug them into our equation here. Now, another way is just as we were dealing with calculating the enthalpy for a reaction would be you have your enthalpy for the entire reaction, and that was equal to the sum of a series of reactions that when you add those reactions together, you get the reaction of interest. We can do the same thing with the Gibbs free energy. And the reason we can do it with both of those, as well as for our entropy, is that the Gibbs free energy, the change in enthalpy, and the change in entropy are all state functions. They only matter where you start with and where you end. And so we can pick any path that we want. And so if we pick a path that is comprised of a bunch of separate reactions, but those reactions all add together to get our overall reaction, then we can use them to calculate the change in our state function, in this case, the Gibbs free energy, at any temperature which these other reactions were done at. So you would need to, if you're not working at 25 degrees Celsius, you would need to have Gibbs free energies at the particular temperature for a variety of reactions that you can add together to get your overall reaction, but the concept still applies. Now, the change in the Gibbs free energy of formation, also called the standard free energy of formation or the free energy of formation, which would be written as delta G sub F superscript naught, is the change in the free energy when 1 mole of a compound is formed from its constituent elements in their most stable elemental form, also called their standard state. This is the exact same standard state that we were using for calculating our enthalpy of formation values. So it's the elements in their most stable elemental form. Again, it's 1 mole of compound, just as it was when we were talking about our enthalpies of formation. So because of this, just as we saw with our change in enthalpy of formation values, the free energy for the formation of pure elements in that standard state is 0. So the change in enthalpy of formation for hydrogen, as we had previously said, was 0 because the change in enthalpy of formation that we had been looking at was the difference in energy between the current molecule and the element in its most stable elemental form. So if we're looking at hydrogen, the difference in energy between hydrogen as a gas and the elements that make it up in their most stable elemental form is 0 because it's already in its most stable elemental form. The same idea applies for the Gibbs free energy. The Gibbs free energy of formation is the amount of energy that's required to form the molecule from its elements in their most stable elemental form. And so hydrogen, H2, is already in its most stable elemental form. So the Gibbs free energy of formation, or the standard molar free energy of formation, for hydrogen is 0. For oxygen, O2, it's also 0. For nitrogen, N2, it's 0. Carbon in the form of graphite is 0. Everything else is going to have a value that is not 0. They can be positive, they can be negative, they can range by quite a bit, but they will generally not be 0. The ones that are typically 0 are the ones that are the elements in their most stable elemental form. Now the Gibbs free energy, as we had said before, is sometimes called the chemical potential. This is the amount of work that we can get out of a system. So we can look at a particular reaction, let's say the formation of methane, right, to try to figure out how much energy we could get from that. So we're taking carbon in the form of graphite reacting with hydrogen as H2 to form CH4. If we look at the process, the change in enthalpy of reaction is exothermic. So the delta H value is negative. This tends to lend itself to having a negative delta G, which is good for the spontaneity of the reaction. Entropy, on the other hand, the change in entropy of the reaction is also a negative value. This tends to make the reaction unfavorable. And so this tells us that at some temperature there will be a change from the reaction becoming spontaneous at low temperature and non-spontaneous at high temperature because of the entropy term. So at 25 degrees Celsius, though, the reaction is spontaneous. The amount of Gibbs free energy is negative 50.5 kilojoules per mole. So if we have our reaction going here, it's going to release a good amount of thermal energy, but some of that thermal energy gets lost to the surroundings. So not all of it is going to be useful. The difference between the thermal energy that is lost to the surroundings in order to make the reaction spontaneous, we take that's essentially our entropy term. We're sort of paying our entropy burden. So that minus our change in enthalpy gives us our Gibbs free energy. The Gibbs free energy is the maximum amount of work energy that we can get out of a process. So in this case, the Gibbs free energy is less than the change in enthalpy because some of the released heat energy is lost in order to increase the entropy of the surroundings. So because the entropy of the system goes down, we need the entropy of the universe to go up, at least according to the second law of thermodynamics, and so we have to create greater entropy in the surroundings. So that's what happens with this reaction. Some of the energy gets lost in making the reaction spontaneous by increasing the entropy in the surroundings. Let's now look at how you would use tabulated data to calculate your Gibbs free energy values. So there are two equations. We could do the Gibbs free energy, our delta G is equal to the sum of the coefficient in front times the Gibbs free energy of formation for our products minus the sum multiplied by their coefficients times the Gibbs free energy of formation for the reactants. Okay, so essentially our products minus our reactants. That's one method. The other method is we can calculate it, and this works for any temperature. The first one really only works for whatever temperature you have in your table, and this table is done at 25 degrees Celsius. So the other method is your delta G naught is equal to delta H naught minus T delta S naught, and these are all for your reaction. And up here, this was also for your reaction. So to calculate those values, what we will need to do is follow the general trend of our products, the sum of our products minus the sum of our reactants. So we can sort of set up a little bit of a sort of pseudo table to calculate these out. The delta G naught reaction. If we look at using our process here, we would add up all of our products and then subtract that from the sum of all of our reactants. So we have carbon dioxide, we have water, we have CH4, and we have 2O2. Okay, so I'm going to look up my value for CO2. So in our table, carbon dioxide is located here. So we're going to be grabbing these values. Our oxygen is located here. You'll notice that the G, the Gibbs free energy of formation and the enthalpy of formation are both 0, but our entropy value is not 0. Our water is at the bottom. And then our last value is the methane. Now, another important thing to notice about the table is the units. The unit for here, for both the G and the H, is kilojoules per mole. The unit for the S is joules per Kelvin times mole, or mole Kelvin, however you want to put the order of the bottom. The main important thing there is that your H and your G are both in kilojoules, your S is in joules, and this is what you'll find for most tables. So when we're using our second equation, this one right here, we need to be careful to make sure that we convert our S into kilojoules before we do our calculation. But we can calculate our Gibbs free energy, products minus our reactants. So our value for carbon dioxide for the Gibbs free energy from the table is negative 394.4. We will add that to 2 times the value for water, which is negative 237.2. Okay, that is all of our products. We will now subtract the value for our reactants. So methane is negative 50.8 plus 2 times the value for our oxygen. The Gibbs free energy of formation for oxygen is 0 because oxygen is already in its most stable form. If we plug this into our calculator, we'll get negative 118 kilojoules per mole. Okay, if we do our delta H of reaction, that's again products minus reactants, so I'm going to just line them up with what I had for the Gibbs. So the CO2 is negative 393.5 plus 2 times the value for water is negative 285.8. Okay, that is the end of my products minus the sum of my reactants, negative 74.85 for methane, plus 2 times, again we get 0 because of how the enthalpy of formation is defined. Plug this in, you get negative 890.25 kilojoules per mole. Okay, last, calculating out our delta S for reaction. It's again products minus reactants, so lining everything up, we get for our carbon dioxide 213.6 plus 2 times the value for water, 69.9, minus the value for our products, 186.19, plus 2, and this time, because we're talking about entropy, it's not entropy of formation, it's just entropy. And so our value for oxygen will actually have a number that is not 0. So it's 205.15 joules per mole Kelvin. Okay, so plugging this all in, you'll get negative 243.09 joules per Kelvin times mole, or you could do mole Kelvin. Okay, now we could calculate our Gibbs free energy using the H and the S from our second equation, right, the one that's right here. So this would be equal to negative 890.25 kilojoules per mole minus our temperature, which is 298.15, right? It's 25 degrees Celsius. And then this, the temperature, this is Kelvin, times our value for entropy. But the value that we worked out before was in joules per mole Kelvin. We need to convert this into kilojoules. So we can shift the decimal place 3 to the left. Shift the decimal place 3 to the left, and we'd come up with negative 0.24309 kilojoules per mole Kelvin. Okay, if you plug this all into your calculator, you'll get negative 817.77, which rounds to the value that we got before. Right? So you can calculate it either way, you'll end up getting the exact same answer. Sometimes you'll get slight differences like we did here, but that is generally coming from some sort of a rounding error or experimental uncertainty in your end value.